versus online?
Yeah.
I don't know. I was also initially very enthusiastic about this. I was attending a lot of talks, and then at some point I got very tired.
Right.
I hope this is not going to YouTube.
This is going to YouTube now. Now it has.
What, Sankha?
What?
She's asking if you don't want your talk to go on.
No. I'm asking about this particular comment that I just made.
I hope at least Shayantan joins.
Let's see. He should join. Sir called me about a couple of hours back.
Whether he is able to join or not.
No, he was asking for the link, so I sent him the link.
Okay. I sent an email this morning.
Yeah, I know. I mean, he must have misplaced it.
Right. Purvita, now we can't see you. So when I sent your abstract in that email, I did not realize that the symbols were missing. I normally just send an email and then you don't do anything. Yeah, you forget that you are also a recipient and you should check. So what happened with that? Like, was it not PDF generated or what happened?
So this is something that I was worried about when I was writing the email. So, in Chrome, you can put an extension to text extension to your Gmail.
Oh.
So that it gets compiled text gets compiled inside your email body. So I did that. While I was doing that, I thought that this may not go through. But anyway, that is exactly what happened.
Okay, I got it from my computer.
Hey Purvita, before anybody else joins, so मोदक देने हैं, किस घर में लाके दूं तुम्हें? स्मिता आ रही है अभी.
Okay.
प्रसाद कहाँ पे देना है? टाइप 4 या टाइप 3?
टाइप 4 पे सब लोग है, मैं अकेली हूँ यहाँ पे.
तो कहाँ पे उसे भेजूं बोलो?
टाइप 4 is good because I am here by myself.
नंबरची काही गरज नाही आहे. लाईन 36 मधलं सेकंड लास्ट मध्ये. Okay, so people are joining now.
YouTube is also like it's working, right? YouTube live. Shankara, you don't want YouTube live or?
No, he's okay with that.
It's okay.
Yeah,
because I just hear some of the like bit of the sentence, not much. I was working on, yeah.
Shayantan, at least today we can see you in a talk.
Okay, then. Okay, then it would take 2 minutes.
Yes.
Okay.
Okay.
Let's wait for a couple of minutes. I've also started wondering with this low attendance, like what's the purpose of running a seminar series like this?
Okay, you are going to chair today, right?
Oh, yes, sure. I haven't prepared, but I will do it.
Like for me, it is a big.
Yeah. That's okay. I will do it. Well, there is no information provided by the speaker.
But you know much, I guess.
There is
That what is provided.
not much information to provide.
So, where did you do your PhD? At least that much I can say.
Okay, so that is Penn State.
Penn State, right.
So Shankoda is okay. We need to make Shankoda co-host, right? Otherwise,
No, I think I can share my screen.
Yeah, he can. Like this
he
is
can.
my.
Oh, that is good.
Yeah.
Yeah,
So I think you can see my screen now.
yeah, we can.
Yes, we can. So, shall we start?
I guess yeah, we can. Yeah.
Okay, welcome everyone. It's our great pleasure to have Professor Sankha Basu from IIIT Delhi to deliver a talk in logic webinar. Yeah, he's going to speak about left variable inclusion and restricted rules companions of logics. Well, yeah, so his specialty is non-classical logics and paraconsistent logics. And over to you, Shankada.
Thank you, Amit. So Amit and Purvita, thank you both for inviting me to give this talk. So let's go ahead, get started. So today I'm going to talk about left variable inclusion and restricted rules companions of logics. This is a joint work with Professor Mihir Chakraborty. Okay, let's see. Okay, so here's the scheme for this talk. So I'll have to disclose some preliminaries before I can go ahead and get started. Thereafter, I'll talk about a known logic, PWK, it's paraconsistent weak Kleene logic. On the way, I have to talk about the general idea of infectious logics and also the algebraic concept of Ponca sums. And then we will come to variable inclusion logics, where I'll discuss two kinds of variable inclusion, the left variable inclusion and the right variable inclusion. After that, we'll go into semantics and then the intuitionistic version of paraconsistent weak Kleene logic. So we call it IPWK, intuitionistic paraconsistent weak Kleene logic. And then finally, we'll come to the restricted rules companion that we defined in our recent paper and discuss its relationship with the logic of left variable inclusion. And finally, we will end with a note on paraconsistency. Okay, so first of all, the preliminaries. So this is mainly so that we are all on the same page. This is all known information. So there are various different ways of presenting a logic. So this is mainly the notation, etc., that we will use throughout the talk. So first of all, we have a logical language. So logical language consists of the connectives or the logical operators. And as we know, each connective or logical operator will have its own arity. So for example, negation is unary, conjunction is binary, and so on. Then we have a set of propositional variables, which we will denote by V. Now, given a logical language L and the set of variables V, the formulas are defined as usual inductively. So we will have a formula algebra that we will denote by boldface FM. This is an absolutely free algebra of type L over the set of generators V. So this part we are borrowing from the domain of abstract algebraic logic. People working in abstract algebraic logic generally write in this fashion. The universe of this formula algebra is going to be denoted as regular face FM. So they're basically the same. Boldface FM is the algebra, and regular face FM is just the universe. Next,
so
we talk about,
question here. What is the difference between free and absolutely free?
So absolutely free algebra is something, well, it is free algebra. So if you ask some people, they will say there is nothing called an absolutely free algebra. But if in the texts on universal algebra, you will find this concept. So the idea is that this is the term algebra. And if you define any function from the set of generators to another algebra of the same type, then it can be, there is the universal mapping property. It can be lifted up to a homomorphism of the entire algebra. So that is just the concept of absolutely free algebra. You might as well call it a free algebra, because I have asked other logicians and they have said, I don't know anything about an absolutely free algebra. But I'm borrowing this term from the recent work in this domain of abstract algebraic logic. It's also there in the in Sankha textbook on universal algebra. So this is, I think it is used sort of interchangeably, the free algebra and absolutely free.
Mm-hmm.
Anyway, next we come to the consequence relation. So it's a relation from the power set of FM, the set of formulas. So sets of formulas to formulas as we usually denote, or as we usually define. Now we will assume in this talk that this consequence relation satisfies the Tarskian axioms of reflexivity, transitivity, and monotonicity. Now, one other property that we will assume for this substitution is, the consequence relation is structurality. So first we need to describe the concept of a substitution. A substitution is just a function from the set of variables to the set of formulas. Now this can then be lifted up again, because boldface FM is this absolutely free algebra. It can be lifted up to a unique endomorphism of the formula algebra. Now a consequence relation satisfies structurality if this property C4 is there. So for any substitution and any set of formulas, and the formula phi, if sigma entails phi, then the substitution function applied on sigma also entails the substitution function applied on phi. So the formula resulting from the substitution function applied to phi. Now, finally, we come to the definition of a logic that we will use. A logic in a language L is this pair which consists of the formula algebra and a consequence relation, so which we are denoting here as this turnstile S. We will drop the subscript S whenever there is no need, there is no chance of any confusion. So we will assume that this turnstile S is a substitution invariant consequence relation on FM. We assume C1 through C4, all of these conditions. And lastly, a logic is said to be finitary if its consequence relation satisfies this property, that whenever sigma entails 5, there exists a finite sigma prime subset of sigma such that phi can be obtained from sigma prime, can be derived from sigma prime. So again, in this talk, for most of the logics, in fact, all of the logics that we will come across in this talk, we will have a finitary logic. Okay, so that's about logics. Now, this next concept is about logical matrices. So, a logical matrix for a language L or an L matrix is a pair which consists of an algebra and a set F. This set F is a subset of the universe of the algebra A. This algebra A can be called an algebraic reduct of the matrix, and F is a filter or the set of designated values. So if you, for example, if you take a Boolean matrix would be, you take a Boolean algebra and the set of designated elements will just be the set containing the element 1, that is the top element. Now, we might as well define here a trivial algebra because we will come across this in the later part of the talk. A trivial algebra is one with a one element universe. All trivial algebras of the same type are going to be isomorphic. This is not hard to see. And for this work, we have denoted any trivial algebra of type L by one boldface 1 sub L, and its universe we have denoted. So the unique element that is in the universe is omega. We will again drop the subscript L whenever there is no chance of confusion. So a trivial L matrix is the matrix consisting of the trivial algebra of type L, and the entire domain is the set of designated elements. So there is only one element, that element is designated. Now, given L and V, so we have a logical language and a set of variables, and an L matrix AF. Each formula phi has a unique interpretation in that algebra A. So this is determined by the assignment that is given to the variables in the formula. So algebraically, this means we have a function, a homomorphism actually, from the formula algebra to the algebra A. And V of phi is the interpretation, so to say, the interpretation of the formula phi in the algebra A. So this kind of a homomorphism can be called an assignment or valuation. Now, given a logic S in a language L, an L matrix AF is called a model of this logic if for every valuation and every sigma phi, sigma being a set of formulas and phi a formula, if the homomorphism V, if the valuation V maps each element of sigma into an element of the designated set and sigma entails phi, then V of phi is also designated. So that is what it means for the matrix AF to be, that is what it takes for a matrix AF to be a model of the logic S. Now, the class of all matrix models of S can be denoted by mod S. I mean, this is just the ordinary valuation model that we define in logics, just stated in terms of matrices. So there is nothing new going on here. Next, a logic S in the language L is said to be complete relative to a class of L matrices M if the following conditions are satisfied. So first of all, M is contained in the set of all models of S. That is, whenever each matrix in M is a model of S, and for every sigma set of well-formed formulas and phi a well-formed formula such that sigma does not entail phi, then there is a matrix which is a witness to that. So there is a matrix and a valuation homomorphism that is a witness to the fact that sigma does not entail phi. So such a class of matrix models is called matrix semantics for S. Now, logics can be induced by matrices as well. So we saw that given a logic, there are matrix models of the logic. Now, it can go the other way around as well. So the way we do this is we take a class of L matrices M, then we define a logic where the consequence relation is defined in the following way. So again, take sigma as a set of formulas, phi a well-formed formula. We will say that sigma entails phi if and only for each member of the class of L matrices M, and for all valuations V from the formula algebra to the algebra A, V sigma is a subset of F, which means that each element of sigma is designated, implies that V of phi is also designated. So in this way, if we can define the consequence relation, we immediately have a logic. And we say that this logic is induced by the class of L matrices M. Now, instead of a class of L matrices, you can also take a single matrix, and you can say that, okay, this you can define a logic which is induced by that single L matrix. Now then, it is again easy to see that a logic is complete relative to a class of L matrices whenever the turnstile of the logic, that is the consequence relation of the logic, is equal to the consequence relation that is obtained from the L matrices. So the logic induced by the class of L matrices is the same as the original logic. So then we say that the logic is complete relative to the class of L matrices. Okay, so next we come to this interesting logic, paraconsistent weakling logic. So here the logical language consists of conjunction. I'm just going by the intended interpretations. Conjunction, disjunction, negation. 0 and 1. 0 is supposed to denote falsity and 1 is supposed to denote truth. The arities are as usual. Now, WK is the L algebra, which is given by these tables for conjunction, disjunction, and negation. Then we can have, as before, we can have boldface FM as the formula algebra of type L over a countable V. That is, the set of variables is countable. Now, PWK can be described as the logic FM turnstile PWK induced by the matrix WK 1 omega. So this means that we take this algebra, this WK algebra, and the set of designated elements is 1 and omega. Okay, so then this means that gamma entails phi if and only for all valuations B from Fm to WK, if each element of gamma is either 1 or omega, this implies that B of phi is also 1 or omega. Now, there are some interesting things to note from this these weak-cleaning tables, but before going into the next slide, I just want to point these out a little bit. So if you look at these rows and columns of omega, you see that whenever omega is composed with any other element, it immediately becomes omega. It's true for conjunction, it's true for disjunction, it's true for negation. So this omega is in a sense an infectious element. So whenever it enters the scene, it just absorbs every other truth value. And if you delete the rows and columns for omega, you see that the rest is just Boolean. So 0 and 1, these are classical truth values. And omega is an infectious element. So hold on to that thought of an infectious element, because we are just about to go into a little bit of a digression into infectious logics. So PWK is a member of this family of infectious logics. So infectious logics can be intuitively described as logics which have an absorbent, infectious, or contaminating. All these terms have been used in the literature. Absorbent, infectious, or contaminating truth value. That is a truth value that is assigned to any formula whenever it is assigned to any of its subformulas. So as soon as a propositional variable assumes the value, assumes this infectious truth value, any formula that you construct with this propositional variable will have the value omega, that is the infectious truth value. Now, the other thing to notice, let's go back to the tables again. instead of designating both 1 and omega, that is the classical truth value 1 and the infectious truth value omega, if you just want to designate 1, you still get an infectious logic, but with a little bit of a difference. You are not designating the infectious truth value. So that is known as Bochvar's logic of nonsense. This is also there in the literature. This is another example of an infectious logic, and there are plenty of other infectious logics. So, for example, there is this Halden's logic of nonsense as well, which is basically Pwk. You are designating both 1 and omega. Now, it is quite easy to check that if there is an infectious truth value, if you designate that infectious truth value, you get a paraconsistent logic. An example of that is Pwk itself, because I mean, you can have P and not P, P being a propositional variable. You can have P and not P. Both will be omega. So therefore, P not P, the set P not P will be designated. And then you can have another variable Q, which could have the value 0. So therefore, then P not P will not entail this Q. So therefore, your premise set is designated, but your conclusion is not designated. You can have a situation like that. And whenever you have P not entailing everything, you have a paraconsistent logic.
Sankha, may I ask something? I had some
Sure.
doubt. Actually.
Sure.
In the table, please go back to the table.
Sure.
Yeah. Actually, here 0, 1 are playing the role of top and bottom, just like in other logic. And omega is in between them or something else?
No, omega is not in between them. So I'll come to that. So I'll describe what is going on with omega.
Okay.
Yeah, in a few slides, I'll describe how to actually see this omega in relation with 0, 1.
Okay. Thank you.
Okay, so the other situation is if you do not designate this infectious truth value, like in Bochvar's logic of nonsense, you get a paracomplete logic, which means that the law of excluded middle will fail. And similarly, you can see this as the OR introduction, that is P or Q follows from P, will also fail in such situations. So I'll leave it at that. It's not a very hard thing to check. I'll move on. So how do we actually see this this infectious truth value? What are the possible interpretations? There have been many, in fact. So here are some. So first is Bochvar and Halden. They interpreted this infectious truth value as nonsense. So in Bochvar's and Halden's case, the infectious truth value is assigned to those sentences that are neither true nor false and hence are truth value gaps. Now, fitting, on the other hand, had an epistemic interpretation. So imagine that you have a set of experts who are trying to opine on a particular statement, and they might have both opinions for a particular statement or no opinion about the statement. So you can have an infectious truth value for those kind of statements for which there is no opinion or both opinions. Now, Ferguson had another interpretation. This is in terms of computational failure. So a computer may fail to retrieve the value of a given sentence. So imagine a program or a computer which is tasked with finding the value for a given sentence. Now, it can return true or false, but what if the program or the computer crashes while it is retrieving? So then what do we say about that sentence? Do we say it is true or false? We can't say either. So therefore, this is the computational failure interpretation. And then Beale gave another interpretation, which is off topic. So the infectious value is assigned to sentences which are off topic. Suppose you are talking, to understand this, so suppose you are talking about the theory of numbers. Now somebody says that 2 is prime, or the sky is blue, or some such thing, which is the sky is blue is not part of your theory. It is off topic. So then what do you say about that kind of a statement, which has an off topic component? So then you can assign an infectious value to it. So basically it means just no opinion. Okay, so that's all about infectious logics. Now on to Purbita's question about how is this omega, the infectious truth value, to be seen algebraically. So in order to do that, we have to enter into the domain of Ponca sums. So the abstract definition starts with a directed system of algebras. So a directed system of algebras consists of, first of all, you have a joint semilattice. The purpose of having this joint semilattice is indexing. So the joint semilattice is going to serve as an indexing set or an indexing algebra. Now you have a family of algebras of the same type with disjoint universes. For each element of the indexing semilattice, you have an algebra. We call it A sub I. Now we also have a bunch of homomorphisms, Fij, which go from Ai to Aj whenever I is less or equal to j in that indexing semilattice. Now the resulting set of this set of homomorphisms will have to satisfy two conditions. First, if you have Fii, that is the identity homomorphism, and whenever you have I less than j less than k, then Fik is the composition of Fjk and Fij. So you have this is a directed system of algebras. Now, what do we do with this? What we do with this is a Ponca sum. So the intuitive idea of a Ponca sum is the following: that you have a class of algebras of the same type. Can you glue these algebras together into a bigger algebra so that some of the properties of the original algebras are transferred to this big algebra, this glued up big algebra? So what you do for that is this: you take a directed system of algebras. Remember that I is a joint semilattice. So therefore, whenever you have a bunch of elements, there is a least upper bound. The Ponca sum of X is this algebra with the universe. The universe is just the union of all the universes of the algebras that are in the directed system. Now, what do we do about the basic operations of this algebra? This algebra is also going to be of the same type as the original algebras in the directed system. So this is what we do. Suppose we have A1 through AN elements taken from the algebras of this directed system. Now, the operation that will be defined on these elements A1 through AN in the Ponca sum is dependent on the homomorphisms that were there in the directed system. So what we do is we take this A1 belongs to some AI1, A2 belongs to some AI2, some algebras, and AN belongs to AIN. Since I is a joint semilattice, there is a J which is the least upper bound of all these I1 through IN. So we'll basically export all these elements A1 through AN into the elements of the algebra indexed by J, that is the least upper bound. So that is what is happening here on the right-hand side. We have Fi1j of A1. This is the exporting of A1 to the corresponding element in the algebra AJ. And then similarly for the other elements, A1 through AN. And then in that algebra AJ, you actually apply the operation F. Okay, so this is exactly what is happening in a Ponca sum. So you first export all the elements to the algebra which is indexed by the least upper bound, and then do the operation. Now, up to this part was defined by Ponca in 1967. In the last part, in the last item, the case for nullary operations or constant terms was also added. So this was for all basic operations with arity greater or equal to 1. Now, in case you have a nullary operation or constant, just like we had in case of Epwk, we had 0 and 1. So what do we do here? We, in this situation, we need to assume that the indexing semilattice has a bottom element. And for each nullary operation, we basically just take the corresponding nullary operation in the algebra indexed by the bottom element. So that is the only change that happens in case you have nullary operations. Okay, now I still haven't answered Purvita's question, so let me go ahead. Now, before I can answer that question, there is some generalization of the directed system of algebras into directed system of matrices. So this was all in the 1960s and 80s. So 1967 and 1987. This is recent. In 2021, this was generalized, or this definition or this idea of directed systems of algebras was moved into matrices. So nothing different here. If you have you still have a joint semilattice, you have a family of matrices now instead of algebras. So you have AI, Fi. These algebras are of the same type with disjoint universes as before. The homomorphisms are also as before, except this one condition that we have to add, that whenever we apply a homomorphism to, so Fij is a homomorphism from Ai to Aj. Now it also acts on the set of designated elements, and this result is a subset of the designated of the set of designated elements in Aj. So we just have to make sure that the designated elements are also transferred to designated elements in the algebra Aj. And then the rest are absolutely identical conditions. Now then we can define Ponca sums of matrices as well. So basically this is just, you have a directed system of matrices. The Ponca sum of this the set of directed system of matrices will be the matrix, where the algebra is the Ponca sum of the algebras in the matrix, and the set of designated elements will be the union of all the designated elements of all the matrices. Now then, given a class M of matrices, PLM, that is the Ponca sum, the PLM will denote the class of Ponca sums of directed systems of matrices in M. So of course, I mean, if we are given a class of matrices, we cannot automatically assume that the class is a directed system, but we can take the directed systems of matrices in M and then construct their Ponca sums. And PLM denotes the class of all those Ponca sums of directed systems of matrices in M. Now, we come to a special case, and this is where I will answer Purvita's question. So suppose this is a special case. Suppose we take an algebra A of some type L, and 1 is the trivial algebra of the same type. Now, the two-element family A1, which just has the identity endomorphism and the unique homomorphism from A to 1, is a directed system of algebras. So A1 is a directed system of algebras, and then you can construct, therefore you can construct the Ponca sum of this directed system of algebras, and this is denoted by A plus 1. So this is the algebra A plus 1, where the universe is A union omega, the universe of A and the unique element in the trivial algebra. For each n-ary basic operation, you have to do F A plus 1 of this A1 through AN will be the same thing if all the A1 through all the elements A1 through AN are in the algebra A, then you just normally operate on them using the operation in the same operation in A. Now, if any of the elements is omega, that is an element of, that is the element of the trivial algebra, the whole thing becomes omega. So this is exactly what is happening in case of infectious logics. So whenever one thing is omega, one component is omega, the whole thing becomes omega. So otherwise, everything stays within the algebra A. Okay, so now using that, well, again, this can be lifted up to matrices as well. So you take an L matrix AF and the trivial L matrix, and this is a two-element family of the two-element directed system of matrices, and you can construct the Ponca sum of this directed system of matrices. This will be just A plus 1, the Ponca sum of A and 1, and F union omega will be this set of designated elements. Now, the class of Ponca sums, this was proved in 2017, the class of Ponca sums of Boolean algebras is a model for PWK. And in particular, this algebra WK1 omega that we saw before is actually the Ponca sum. This matrix WK1 omega is the Ponca sum of the matrices B2, 1 and the trivial Boolean algebra. B2 is the two-element Boolean algebra. So you just take the two-element Boolean algebra and the trivial Boolean algebra, which has one single element, and you take the Ponca sum of these. The resulting algebra that you get is definitely not a Boolean algebra. This omega is is outside the two-element Boolean algebra. It is neither, this omega is neither below 1 nor above 1, but this omega is somewhere outside. It's another algebra. You have somehow glued together the two-element Boolean algebra and the one-element Boolean algebra, and that is the algebra WK. Purvita, have I answered your question?
Yeah.
Okay. Now we come to this. Now hopefully I'll have enough time to explain why I went through all these elaborate constructions. So we come to the variable inclusion logics. We start with PWK again, because PWK is a prime example of a variable inclusion logic. So this is the kind of the syntactic version of PWK. So we take the logical language to be and or not, conjunction, disjunction, negation, 0, 1 as before, B, boldface, FM are as before. The PWK is the logic induced by WK1 omega that we saw before. And by CPC, we denote classical propositional logic. Now, we just make two little notational definitions. So, where phi is the set of variables occurring in the formula phi, and this is extended to where gamma, variables in gamma, so which is just the union of the set of variables in each formula. And then this is a result from 2014, which was by CUNY and Carrara. And this is a characterization result for PWK. And this was really a motivating factor for these logics of variable inclusion. So take any gamma union phi in FM. Gamma is a set of formulas, phi is a formula. Now, gamma entails phi in PWK if and only if there is a gamma prime subset of gamma such that variables in gamma prime are contained in variables in phi. So there is a subset of the set of premises such that each element of this subset has its variables contained in the set of variables in phi. So in other words, this gives kind of a, and this gamma prime entails phi in CPC. So this is a kind of, it has a relevant flavor. So your conclusion cannot be completely different from your set of premises. It has some variable sharing, must have some variable sharing properties. But it's not really a relevant logic. I mean, this will be clear in a moment. Moreover, since this classical proposition logic is finitary, we can always find a finite such gamma prime. So we will, whenever phi is conclusion from a gamma, in PWK, there is a finite gamma prime, finite subset gamma prime of gamma, such that variables in gamma prime are all inside the variables of contained in the conclusion, and gamma prime entails phi in the original logic, that is CPC. Okay, so now we come to a generalization of this concept. So logics of variable inclusion, as I mentioned earlier, there are two kinds of variable inclusion possible. One is the left variable inclusion, the other one is the right variable inclusion. So this is exactly a generalization of the case for characterization for PWK. So L is the type or language being set of variables. FM, boldface FM, regular face FM as before. Now you take any logic S. The left variable inclusion companion of S, this is denoted by SL, and the consequence relation of this logic is defined in the following way. So for any gamma union phi subset of FM, gamma entails phi in this left variable inclusion logic if and only if there is a gamma prime such that variables in gamma prime are contained in variables in phi, and gamma prime entails phi in the original logic. So this is an immediate generalization of the characterization theorem proved by Cuny and Carrara in 2014. So this is left variable inclusion. Now we can also define a right variable inclusion. So it goes exactly the same way. We have SR, and in this logic, gamma entails phi if and only if gamma entails phi in the original logic, and the variable inclusion is reversed. Variables in phi are contained in variables in gamma. Or there is a sigma subset of gamma, and sigma is a set of inconsistency terms for S. Now, of course, this talk is not about the right variable inclusion, but I can tell you this, that by inconsistency terms, it means that so every formula can be entailed from this sigma. So this has direct links with LFIs, the logics of formal inconsistency, and so on. So that's a subject for another talk, and I'm not going to say anything more about right variable inclusion. So left variable inclusion and right variable inclusion logics are also known as containment logics, mainly because there is a containment relation between the sets of variables in the premise and the conclusion. Either way, so whether it's right or left. Now, then we come to examples. So by our previous discussion, PWK is the left variable inclusion companion of CPC, classical propositional logic. This was already known when we started working on this, and then we worked on the intuitionistic version of this. Intuitionistic paraconsistent weak-linear logic is the left variable inclusion companion of intuitionistic propositional logic, or IPC. Now, Bochver's logic that I mentioned earlier is the right variable inclusion companion of classical propositional logic. Again, so I'm not going into Bochver's logic. Now, some general properties of SL, that is the left variable inclusion companion. So first is a logic and its left variable inclusion companion, they share the same theorems. So formula phi is a theorem of the original logic if and only if it is a theorem of the left variable inclusion companion. So in particular, that means PWK has all the theorems that classical logic has. But PWK is paraconsistent. It has an infectious truth value in the semantics. The other result is this. Suppose you take a logic and its left variable inclusion companion. Then for any sigma union phi, if the intersection of all the variables in phi and all the variables in sigma is empty, so basically this means that sigma and phi, the set of premises and the conclusion, they do not share any variables, and phi is also not a theorem, then it can be shown that sigma does not entail phi in the left variable inclusion. So in other words, the contrapositive would say that if sigma entails phi in the left variable inclusion companion, then either phi is a theorem of the original logic, or there is some variable sharing going on. Okay, now some recent results, and this explains why we went into the elaborate constructions of the Ponca sums. So these are recent results from a paper published in 2021. The first one says that if you have a logic and X is a directed system of models of this logic, then the Ponca sums of PLX, that is the class of Ponca sums, the Ponca sum of X is a model of the left variable inclusion companion SL of S. The second is, if you have a logic S and M is a class of matrices of the same type as Fm, by that I mean the algebras in the matrices in M are of the same type as Fm, containing the trivial matrix 1 omega, trivial L matrix that is of the same type again. If S is complete relative to M, then SL, the left variable inclusion companion, is complete relative to PLM, that is the class of Ponca sums of the directed systems of matrices in M. So what happens due to that? Well, first of all, PWK, by this time, by now, we are already feeling tired of PWK. I'll come to a different system very soon. But before we leave PWK, suppose M is a class of Boolean matrices containing the trivial Boolean matrix, then PWK is complete relative to PLM. So this is exactly what was proved in an earlier paper on paraconsistent Weakling logic. Now we come to the case of IPWK. This is quite similar, but maybe this will give a better idea because this is developed from scratch. So you take a logical language which consists of conjunction, disjunction, implication, negation, 0 and 1. The rest are as usual. Then any Heiting algebra can be seen as an algebra of type L that is given here. Then you take the class of all Heiting matrices, that is H1. One denotes the set of, so there is only one designated element, and H is a Heiting algebra. Now we know that IPC is complete with respect to relative to H. The trivial L matrix, that is the trivial consisting of the trivial Heiting algebra as its algebraic reduct, is a member of this H. So therefore, by the previous results, we have the left variable inclusion companion of IPC, that is IPCL, is sound and complete relative to the class of Ponca sums of the directed systems of matrices in PLH. We could have just said PLH. Anyway, so IPWK, in part, some more facts. Now, this is, so far I have only talked about IPCL. I have not yet defined IPWK. So in particular, for each Heiting algebra, we can construct this H plus 1, that is the Ponca sum of any Heiting algebra with the trivial Heiting algebra. And we denote this by H hash. We can take the corresponding matrices. The intuitionistic paraconsistent Weakling logic, or IPWK, is now defined using the class of matrices H hash or H sharp. So, so I discussed earlier how we can induce a logic from a matrix or a class of matrices. This is exactly what is going on. So we define IPWK as the logic induced by this class of matrices. Then we can conclude that IPWK is IPCL because of our previous results. So the results proved or shown earlier. Now, just like the characterization theorem for PWK, we also have a characterization theorem for IPWK now. And it reads exactly the same, except that you replace PWK with IPWK and CPC with IPC. The rest is exactly the same. And this is something that follows from the definition of your left variable inclusion companion as well. Lastly, so we now come to the restricted rules companion. So I have about 6 minutes, I suppose. Okay, anyway, so the motivation for this restricted rules companion is as follows. Now, in this recent paper in 2017 by Bonzio, Gilferes, Pauli, and Peruzzi, not only did they prove that PWK is CPCL, not exactly in those terms, but the fact that PWK is CPCL follows from an earlier work by Cuny and Carrara, but they in this paper, 2017 paper, they still did not mention left variable inclusion companions, but they did something else. They gave a Hilbert-style presentation for PWK. And this consisted of the same set of axioms as the classical propositional logic. The only change was the rule of inference. So the modus ponens rule was modified into this restricted modus ponens rule, where it said that beta follows from alpha arrow beta, provided the variables in alpha are contained in the variables in beta. Now, a Hilbert-style presentation of IPWK can be obtained in the same way. So you just take Hilbert-style presentation for intuitionistic propositional calculus and just restrict the modus ponens rule to this one, the restricted modus ponens, and you will get an axiomatization for IPWK, which is IPCL. Now the question that naturally arises over here is it always the case that whenever you have a left variable inclusion companion of a logic, if the original logic has a Hilbert-style presentation, can we always get a Hilbert-style presentation of the left variable inclusion just by restricting the rules of inference? So that is the question that we started to answer in this following way. We first defined the restricted rules companion of a logic. So in this definition, we have called a logic induced syntactically via a Hilbert-style presentation. We have referred to that as a Hilbert-style logic. Now we just take the abstract version of something that we already saw. So suppose this logic S is a Hilbert-style logic, which means it has a Hilbert-style presentation. It is induced by a Hilbert-style presentation. A is the set of axioms, and R sub S is the set of rules of inference. Now, the restricted rules companion of S, we denote this by SRE. The set of axioms stays the same. The set of rules of inference are exactly those where the variables, so for example, like modus ponens, we restricted it to the restricted modus ponens. For every such rule, we will do the same thing. That a rule is of this form. You have some formulas from which something follows. So gamma is a set of formulas, something alpha follows from gamma. So we'll make sure that variables in gamma are contained in the variables in alpha. So just like the restricted modus ponens, so here we had alpha arrow beta in gamma. And we are, by this condition, we are just making sure that every variable on top of the bar is contained in the set of variables that appear below the bar, in the formula below the bar. Okay, so now immediately the examples follow. PWK is CPC-RE. It's the restricted rules companion of classical logic. IPWK is the restricted rules companion of intuitionistic propositional logic. And incidentally, they are also the left variable inclusion companions of classical and intuitionistic logics. Now, let's go into some properties. So suppose you have a Hilbert-style logic, and its restricted rules companion has exactly the same theorems. Just like the left variable inclusion companions, a formula phi is a theorem of this restricted rules companion if and only if it is a theorem of the original logic. Then this is a relation between SRE, that is the restricted rules companion, and the left variable inclusion companion. So far, we are on track towards proving that, yes, the restricted rules companion is the left variable inclusion companion. We are on track, but we have not done that yet. So suppose you have a Hilbert-style logic, then you have SL and SRE both, and then you can show that whenever gamma entails phi in the left variable inclusion companion, in the restricted rules companion, then gamma entails phi in the left variable inclusion companion as well. That is, turnstile RE is a subset of turnstile L. Now the bubble is going to burst. SRE is not SL. So the reverse inclusion does not hold. And it's not very hard to show that. We just came up with this toy example. So here we take a language which consists only of conjunction and disjunction. The set of axioms is empty. We do not take any axioms, and we just have two rules. One is and elimination, and the other is or introduction. Very, innocent looking rules. And then we construct the restricted rules companion of this logic. So here we see that we only need to restrict the first rule, because there is the only chance where we have more variables on top is here, R1. So here we just restrict this rule, saying that variables in beta must be contained in the variables in alpha. Now R2, there is no restriction needed, because alpha also appears here in the bottom. So therefore, it's automatically, a variable restriction is already imposed there. Now we look at this little derivation. So P and Q are distinct variables. So start with P and Q, derive P and Q. It's just the premise. Using R1, we can get P. Using R2, we get P or Q. Therefore, P or Q is entailed from P and Q. Now, since the variables in P and Q are the same as the variables in P or Q, this also goes through to the left variable inclusion. So in the left variable inclusion companion, we still have P and Q entailing P or Q. However, we can't do the middle step. We can't exactly do this derivation, but because the way the left variable inclusion companion is defined, we can have this entailment. But we can't do this in the restricted rules companion, because we can't apply R1. We can't replace the application of R1. There is no way to go from a conjunction to a disjunction without breaking the conjunction. And we cannot break this conjunction, because our rule R1 got restricted to this, that the variables in beta must be contained in the variables in alpha. And we took Q to be distinct from P. So therefore, in this very simple case, we see that RE is a proper subset of, turnstile RE is a proper subset of turnstile L. We can do something in turnstile, in the left variable inclusion companion, but we can't do that in the restricted rules companion. So therefore, SL is not equal to SRE. Now, here is some way of making sense of this phenomenon. So the restricted rules companion of a logic enforces a variable inclusion locally. At each step of a derivation, you have to make sure whenever you are applying a rule of inference, you are made to check the variable inclusion. But the left variable inclusion companion outsources the steps of the derivation to the original logic. And then globally, there is this variable inclusion restriction. So therefore, there is always this difference. So whenever you have to go through each and every step, you may not be able to do it, but let's say, I mean, as we saw in the previous example, we can still have it globally. So P and Q entails P or Q globally. It's there because the variables come back. You delete a variable, you introduce it back, and you are okay. But you can't do that in a restricted rules companion. Okay, now when are they the same? So the question is there a necessary and sufficient condition when SRE is equal to SL? We already know that SRE is contained inside SL. Whatever you can do in SRE, you can do in SL. So we looked into this. I mean, this was accidental. We started thinking about the deduction theorem. The deduction theorem and its converse. Sometimes the pair is also known as the deduction detachment theorem, which says that sigma union alpha entails beta if and only if sigma entails alpha implies beta. So we proved that if the original logic satisfies has the deduction theorem, then the left variable inclusion companion also has the deduction theorem. So the deduction theorem carries forward. But the converse is not so lucky. So if the original logic has the converse of the deduction theorem, then the left variable inclusion companion only has the restricted version. So sigma entails alpha implies beta, and the left variable inclusion companion implies that sigma union alpha entails beta only if the variables in alpha are contained inside the variables in beta. Both of these are not, I mean, the proofs of these are not very hard. I mean, one can probably do it very easily. But anyway, that's the case. Now, these two results give us a key to a sufficient condition for SL equals SRE. Now, suppose you have a finitary Hilbert style logic such that you have modus ponens, and suppose the deduction theorem holds in S. Then the restricted rules companion of S coincides with the left variable inclusion companion of S. So it is the deduction theorem and the modus ponens. Well, you can see it as the converse of the dt as well. So modus ponens is something like the converse of dt. If those are there, then you can immediately have. In fact, it is better to say it in terms of modus ponens because you know. Well, even with the converse of deduction theorem is not a problem. You either restrict the modus ponens or you restrict the converse of dt. So they are equivalent. So now the fact that PWK is CPCL and CPCRE at the same time, that is the left variable inclusion companion of classical logic, coincides with the restricted rules companion of classical logic, and same for the intuitionistic case, can now be seen as corollaries of this theorem, because in both classical logic and intuitionistic logic, we have the deduction theorem. Modus ponens is a rule of inference. Therefore, it is not a surprise that the left variable inclusion companions of these logics coincide with their restricted rules companions. Now, there is another logic that we proved in the paper to be, I mean, we showed that we discussed another logic, and in that case, the restricted rules companion did not coincide with the with its left variable inclusion companion with respect to time. I mean, I won't go into that. I mean, it's not going to be possible. So there are other logics which can, instead of the toy example, I could give other logics, well-established logics where the left variable inclusion is not the restricted rules companion. So just let's keep it at that. Now, lastly, I'm going to talk a little bit about paraconsistency. So a paraconsistent, everybody knows, assuming everybody in this call knows what a paraconsistent logic is. But anyway, so a paraconsistent logic is a logic where triviality does not follow from a negation inconsistency, and this is the rule of explosion, and a logic has to invalidate this rule of explosion, the principle of explosion, in order to get a paraconsistent logic. Another rule that is connected to the study of paraconsistency is the law of non-contradiction. So which says that take any formula, not of alpha and not alpha is a theorem. Now CPC and IPC validate both ECQ and LNC, that is the principle of explosion and the law of non-contradiction. But these two are independent of each other. There are plenty of logics which invalidate one but validate the other one. So for example, the logic of paradox is one where LNC holds, the law of non-contradiction holds, but ECQ fails, that is explosion fails. Logic of paradox is a paraconsistent logic, but then there is Lukasiewicz three-valued logic where law of non-contradiction fails, but explosion is valid, so therefore it is not paraconsistent. So failure of LNC alone is not enough to give a paraconsistent logic. However, it is a departure from the classical way of handling a contradiction. So we say that a paraconsistent logic where both ECQ and LNC fail are strongly paraconsistent, and hence the paraconsistent logics where LNC holds can be called weakly paraconsistent in that same vein. Now, if you take logic and its left variable inclusion companion and the restricted rules companion, they're both paraconsistent. So, I mean, the fact that the left variable inclusion companion is paraconsistent was hinted at way before in this talk. Now, the restricted rules companion is a sublogic of the left variable inclusion companion. Hence, they are also paraconsistent. ECQ fails in both of these. However, if you remember, both the left variable inclusion companion and the restricted rules companion, they share the same theorems with the original logic. So therefore, if the law of non-contradiction holds in the original logic, they also hold in the restricted rules companion and the left variable inclusion companion. So here we have a little summary. So if the original logic is not paraconsistent, but LNC holds, then LNC still holds in these companions and only ECQ will fail. So it becomes these companions become weakly paraconsistent. Now, if the original logics are not paraconsistent and LNC fails in them, they will become at least weakly paraconsistent. The companions will be at least weakly paraconsistent. Since LNC fails in the original logics, LNC will also fail in these companions, and therefore these companions will become strongly paraconsistent. So for example, if you take Lukasiewicz's three-valued logic, it is not paraconsistent, but LNC fails, its companion logics will be strongly paraconsistent. If you start with a weakly paraconsistent logic, the companions will be weakly paraconsistent. If you start with a strongly paraconsistent logic, the companions will be strongly paraconsistent. So the gain here is really where you are starting with a not paraconsistent logic. You can either end up with a weakly paraconsistent or a strongly paraconsistent logic, depending on whether LNC holds in the original logic. So that's it. Thank you.
Thanks a lot, Shankara. Are there any questions? Okay, I have a few. Sure. So what is the difference between direct limit and Ponca sum?
I do not know. I haven't encountered direct limits.
Okay, like simple category theoretic directed limits and Ponca sum. It just seemed to be exactly that. Maybe it's just done in a slightly different language, but
it is possible. I haven't encountered direct limits, but okay, I can check. But yeah, so definitely these Ponca sums, they have a category theoretic flavor, so to speak.
Yeah,
there must be a category theoretic version.
Yeah, you're starting with a directed search, and direct limit is basically the limit of that. So
Right.
the only difference I felt that you are just taking the union, and that union a disjoint union?
Yes, because the algebras have disjoint universes.
Yes. So even though it is disjoint union, you are actually taking equivalence classes of all the elements individually, and you are identifying them with their images under those individual morphisms.
Right. Right.
Yeah. So it's essentially you are doing the direct limit construction. Okay. Another thing is this companion thing motivated from model companions in model theory?
I guess not, because there is this whole literature about this infectious logics, and PWK has been studied more so recently. I mean, when this 2017 paper came out, it said that PWK is not studied as much as other Kleene logics. So lately, there has been an explosion in work on these paraconsistent weak Kleene and its related logics.
Okay.
So they are also in the, there is this first degree entailment logic. So there are a bunch of logics in this FDE family, the first degree entailment families. So I think that it has an independent genesis, this paraconsistent weak Kleene, and the characterization theorem could be seen as the characterization theorem for PWK can be seen as a motivating example for the definition of left variable inclusion.
Okay.
So, I mean, I'm not sure if there is, there are these, I mean, if somebody thought in terms of model companions, but I mean, from what I have seen, it is perfectly okay to assume that it has an independent genesis from.
Right. But the same name. Okay. Any other questions or comments?
Let me just add one thing. It is that, I mean, if I'm not sure whether this model companion thing has got something to some relationship with this with these companions. I mean, left variable companions on those. But in our study, what was really interesting for us was that this restricted rule companion and left variable companions, they are not the same. That was really interesting. So, I mean, we should also see whether it has got, I mean, this restricted rule companion logic, whether it has some kind of relationship with, again, model companion. Yeah, perhaps there is no such thing there.
Model companions are not defined for logics, but for theories.
True. Yeah. But ultimately, maybe there is some, because from logics, we can go to some semantics. This Plonka sum type thing is really the semantics. And that gives the algebraic structure. So, and from there, you can pass on to the categories. And so, there may be some thread between this and that. But since here is a difference between the left variable inclusion and the restricted rule companion, there must also be some differences there. I mean, so one can look for, So that is what I would like to stress a little more in Shankha's.
One thing is clear. I mean, if you take the restricted rules companion of a logic, Now, suppose there is this algebraic semantic, the original logic is sound and complete with respect relative to a class of algebras. Immediately you see that the restricted rules companion is sound relative to that, to the class of Ponca sums, those algebras. But you can't get the completeness.
Okay.
So there must be, algebraically speaking, there may be a class of algebras which is just below the class of Ponca sums.
Okay.
And in some cases,
can you repeat that sentence?
Yeah, so there may be a class of algebras which is just below the class of Ponca sums.
Okay.
When the restricted rules companion is not coinciding with the left variable inclusion companion, it is sound but not complete with relative to the Ponca sums. So there may be some smaller class of algebras or some subclass of the Ponca sums that is there. And in some special cases where we see a convergence, there this subclass is just the class of Ponca sums.
Right.
So
some more properties on the semi-lattice, perhaps.
Maybe, yeah, possible.
Yeah,
it's possible. Yeah, some more properties may be needed on the semi-lattice.
And like the omega in PWK, that sounds like a generic element, which is sort of present everywhere. When you study algebraic geometry, and then where is the generic point? You can't see it; it's everywhere. So that is also interesting.
Point at infinity.
Oh no, I did not mean that. Point at infinity also has a very specific location. Like it cannot be somewhere in the middle, but this omega is just everywhere. But when we do something like when we define some function and we don't know, like we have specific images in mind, specific assignments in mind for some elements of the domain, and in the rest cases we don't know what to do, then it is good to assign it value omega and just not bother. So as a dump value also, it seems to serve some purpose. And perhaps that was the off-topic interpretation.
Yeah, maybe the last interpretation, one. Yeah, but that's not the only one. That is the point. This strange element, actually, it can be not only one. It can be a set of such elements. That has already been done, isn't it, Shankha?
Right. Yeah.
So okay, but the genesis of this these kind of elements in categories, I think, is one very important step. Maybe sometimes you can explore. What are the roles of these elements in the categories? In the corresponding
semigroups, people have studied this, like these are absorption elements in semigroups.
Maybe those things we can also look into. That may give a clear picture. Otherwise, the picture comes local. Right. Shankha, you can make it a point also, because Shantan is also interested in categories. So the interpretation of this contaminating element in the categorical setup is something that definitely makes sense, which we have not noticed in all the literature that you have.
Yes, absolutely. I mean, this is a new revelation that has come about. Yeah.
It's good.
Okay, anybody else wants to say anything? Shantan, you have unmuted yourself. Oh, muted. Again muted. Okay.
His hand.
Huh?
In between, Shantan raised his hand. I think.
Okay.
I'm not quite sure.
So you were telling me something. I could not hear that. So that's why I just refreshed the page. Yeah.
Myself, I just I uttered your name. That's
Oh,
all.
I see.
No
Okay, I
question
see.
of that. Yeah.
Okay.
I said that you are interested also in category theory. So what Kuber has said may be interesting for you also. That's fine.
Okay. Purvita, you want to say anything?
So, sir, I just had a question. I just regarding this is just the construction of Plonka sum. This is probably you have mentioned somewhere, but so why do you take the sets to be disjoint? Is it because of the well-definedness of the homomorphism?
Yes, exactly. So
I see.
you
Yes.
just have to export out all the elements to,
Right.
yeah.
Exactly. So your A1, AN, right. Yes. So that's one. That is the one point on only where probably it is getting used.
Yes,
Is the
exactly. So you will
okay?
not be sure about which homomorphism to use if they're not.
Exactly. Exactly. Yeah.
Okay, thanks a lot, Shankada. It was wonderful talk.
Can I just
Yes.
thinking loud? It uh, is there any kind of categorical study of the new algebras which are being formed out of the old algebras? So, for example, IPWK. IPWK is coming from where, Shankar?
IPWK is just the result of following the same construction, starting from
Yeah.
hiding instead of Boolean.
So it is heading plus something. Plus means okay in that sense, loosely speaking.
Right.
So suppose I took the categories here. I mean, where instead of the category of heading algebras, instead of taking that category, taking IPWK. Then these omegas will have some roles there, most probably.
Right.
So maybe the picture will be more clear in the categorical setup.
Right.
Yeah.
Yeah.
Yeah. Okay.
Okay, so next week, I believe it's Shayantan speaking.